Okay, so we start our class now. We are starting from page 258. So if you have your textbook ready with you, just print it and you can refer to the pages. So last time we finished up to here, so we're starting at 7.5, unknown arrival time. So in many situations, it is desired to detect a signal whose arrival time or equivalently its delay is unknown. An example might be a radar system in which a detection indicator aircraft and its round-trip delay is used to estimate range. Because the arrival time, if you multiply it with the velocity, then it becomes range. So uh, arrival time in a lot of situations would indicate the estimate of the range. So a GLRT might be employed as a detector. We now consider this detection problem. So if there is no target, which is H0, then your received signal Xn is equal to Wn, which is the noise only. And then if you have a target, then your signal is a H1, which is a signal plus a noise. So this is the H0 and H1. And then where that Xn is an unknown, it's a known deterministic signal. So remember that whenever we talk about detection problems, we always have to be aware of the signal model, whether it's random signal or deterministic signal. Okay, and then it's over the interval 0 and minus 1. N0 is the unknown delay. So let's go back again. This N0 is the unknown delay. This is a known signal, noise, and this is the unknown delay. Okay, and Wn is the WGN with variance sigma square. And clearly, the observation interval should include a signal for all possible delays, meaning that we still have some knowledge about its arrival time. We don't know exactly what it is, but it will be in the interval 0 to n minus 1. Then a GLRT would decide H1 if this sustains, right? And what that means is we need to do an estimate for this N0. Once this N0 is done, we replace that N0 with the estimated N0 and then put the likelihood ratio P of X conditional N0 hat, because this N0 is unknown. So we have to estimate it and put it in and conditional H1 over Px conditional H0 larger than gamma. And N0 is the maximum likelihood estimator of N0. But however, at this point, we have not talked a lot about the maximum likelihood estimate of anything. I mean, of continuous or parameters. We only do it for hypotheses. So that MLE, we'll talk about later in detail, but we learn about it right now. So we just get a sense of what it is and just some of the things are simple enough so that we can still calculate it. Okay, so it has been shown that by this N0, in another textbook, okay, in another textbook, N0 is found by maximizing this, okay. And how this come from? How does it come from? It comes from, we write this n0 as unknown and write it as p of x condition on n0. We n0. We write it into a likelihood ratio and then maximize it. And then with some simplifications, it will become this. So we maximize this with all possible n0, then you get n0 hat. Hence, we correlate the data with all possible delay signals. What are the possible delay signals? This, right? From 0, 1, 2, all the way to -1. So we correlate the data with all possible delays and choose n0 as the value that maximizes the correlation. To evaluate the GLRT, then we need to calculate this. Okay, and then P of X n0H1. This is what? This is a Gaussian distribution, right? Because the noise is Gaussian. So we write it out as a Gaussian distribution multiplied by when you have a signal that appear, right? It could be from 0 to n0 minus 1, and that is purely Gaussian, because before n0, it's only Gaussian distribution with 0 mean, and then multiply this from n0 to n minus 1. That is a Gaussian distribution with a signal. We call that, now you have a signal. Okay, so then you have a signal, okay, and then from n0 plus to n minus 1, it goes back to the ordinary Gaussian distribution. So it's like you have a noise, and then suddenly you have this S with Gaussian, and then it becomes noise again. So you have one session, second session, and third session. So you write it out, it becomes like this. And okay, so let's continue. Okay, so of course you do some simplifications, put some of the terms. For example, you have multiplication of those things, they are the same. So you put them together, and then you have this, you open that parenthesis, you get x squared, and that x squared combined with that, it's been put together. And the other stuff including x, right? That's here. X and s, because of the square term, when you open it, there is a -2. So this is what happens here. Okay, and then s square. So you have s square. That is what happens here. Okay, so now you have a whole bunch of Gaussian distribution, and then their square root 2 pi sigma square being put together here. And then the other part is the exponent part that includes s. Okay, and So we have this px n0 h1 px h0 equal to multiplication of this that because of what? Because this term is exactly the same as this term. So when you put this whole thing in the numerator and put this in the denominator, you get this cancel out. And what remains is this term goes here. Okay, so now you have this. Then you take log, a common technique. We take log and then let that exponent disappear. So we decide h1 if this is larger than some kind of threshold. But this thing, if you sum it up, this term, it's equivalent to uh, signal energy. Signal energy. So what that means is the signal energy doesn't matter, right? It becomes a constant term inside. So once it's constant, in other words, what we are trying to say is this term, when taking summations, it becomes epsilon. Epsilon has nothing to do. It not relate to n0. We're interested in n0, but it has nothing to do with n0. As a result, that term can be taken out without any relevance. So we decide h1 if this is larger than something. And then, of course, that thing, when you take it out, you put it on the right hand side, it becomes a constant term. And then you have this and you have that. So eventually you get this only. You get this term only, right? Because this term is what eventually stays. Okay, and then some kind of threshold, put it into a single threshold. And also notice that there are some plus and minus things. Those things either cancel out or you change the direction of this. You change the direction of this, right? You have either have a minus 10 in front, so you just change it, things like that. So you can easily take the sign, positive or negative sign, out. Okay, so this says that the GLRT implements a correlation of X with S and then compares the maximum value that obtained when this is the to a threshold. If the threshold is exceeded, the signal is declared to be present and its delay is estimated as n0. In other words, what you are doing is you multiply x, that's your receive signal, right? This is receive. This is what? This is the signal that's known, right? And then what you do is you put n is equal to one value. No, let me reiterate this. You put n0 head as all possible values, which is from 0, then 1, then 2, then 3, then 4, all the way up to n minus 1. And then you see uh, which value of n gives you the maximum value of t, and then let t compare with the threshold, and the n value of n that gives you the maximum value of t is the n0 head. Okay, so that's the detection process. Okay, so if the threshold is exceeded, a signal is declared to be present and its delay is estimated as n0. Otherwise, noise only is declared. Notice that the test statistic may also be written as this. So I think this one is clear. You receive a sequence of signal. You compare with S, but that S is kind of a shifted version, shifted by 1, shifted by 0, shifted by 1, shifted by 2, by 3, all the way to n minus m. And then you you calculate all potential values for this, and then take the maximum. For example, uh, you do an experiment and it gives you 10 as the maximum. Then you say 10 is the n0. And next one you try it, you might get 20. Then 20 is the n0 for this experiment. Okay, so that's the thing. This is very common in signal processing when people are doing sequence detection or do delay detection, particularly in synchronization applications. For example, in communication systems, when transmitter and receiver needs to communicate, they need to synchronize each other with each other. And what is done is the transmitter receiver sends out to each other some kind of PN sequence, and then they calculate the maximum value for the correlation so that they synchronize in time. And the other application is the radar communication. You send out a signal, and the target is hit by the signal and refracted the signal, and then the signal comes back. You want to know the delay of the signal, and that is the delay of the signal is not easy, but you kind of take in the S and then start to correlate with your received signal and see what time delay correlates the best. The time delay that correlates the best is the maximum likelihood estimation of the time delay. Okay, so this implementation is shown. You receive this, and this, remember, this is known, and you are adjusting n0. You're adjusting n0, and then for each time instant, for example, 0, 1, 2, 3, for each instant, you do this and choose the maximum and compare and give the outcome H0, H1. And of course, hypothesis is one thing. Correlation is actually by itself complicated because you have to calculate a lot of multiplication and summations. Oftentimes, this kind of application is complicated. Okay, so there will be reduced complexity version, but we'll do that later. Okay. So GLRT, the block diagram, and then the determination of the detection performance of the GLRT is difficult. We need to determine the PDF of the maximum of the correlated Gaussian random variables. The correlation arises because the same noise samples enter into the sum of successive values of n0. We do not pursue this method further, but refer to example. Okay, so the use may be undesirable in situations where the delay must be determined to be less than the sampling interval. In such case, the test statistic can be implemented by the frequency domain. Okay, so it's shifted to a frequency domain and to a frequency domain correlation. So do it by Fourier transform. The case of unknown arrival time and unknown amplitude can also be addressed. So it is shown that unknown arrival time and unknown amplitude. So decide H1 if this is larger than gamma prime. Okay, so let's see. Okay, I think that's all for this session. We'll take a break and come back soon.